So now what is dimensional analysis? So dimensional analysis is a mathematical techniques which makes use of a study of dimensions as an aid to the solution of several engineering problems. So that's why here the importance of the dimensions of the physical quantities is very important. So you should know the dimensions. Using these dimensions, so we try to solve many engineering problems. So that's dimensional analysis is a mathematical techniques which makes use of these dimensions in order to solve several engineering problems. So you know that every physical phenomenon can be expressed by an equation that will be consisting of variables that is also known as the physical quantities, which may be dimensional or it may be a non-dimensional quantities. Here dimensional analysis does what it does is that it helps in determining a systematic arrangement of these variables in a physical relationship and combining these dimensional variables to form a non-dimensional parameters. So a non-dimensional parameters like so mu by rho vd or vl by nu like this. So various physical quantities are combined to form the non-dimensional parameters. For example, L by D. So this is how H by D. So these are some of the non-dimensional parameters which have been formed by systematically arranging the variables in this which are involved in a physical relationship and thus combining the dimensional variables to form a dimensional parameters. So what is the use of dimensional analysis? So here we can test the dimensional homogeneity of any equation of the fluid motion. So dimensional homogeneity means you know that the dimensions on the left hand side should be equal to dimensions on the right hand side. You can derive the equations in terms of a non-dimensional parameters and to give the relative significance of each of the parameters, and we can plan the model test. So model studies can be done and these experimental results can be used in a systematic manner to analyze the complex fluid flow problems. So that's the use of dimensional analysis. Now coming to the various dimensions of different physical quantities that are used. So what is this dimension? So various physical quantities to describe a given phenomenon can be described by a set of quantities which are independent of each other, and these quantities are known as the fundamental or the primary quantities. So for example, mass, length, time, theta are all the primary quantities, which is mass, length, time and temperature, and all other quantities like area, volume, velocity, acceleration or force, energy, power are all known as the derived quantities, or also known as secondary quantities, because they are expressed in terms of the primary quantities. For example, velocity is length by time, so acceleration is L by t square, force is mass into acceleration. Okay, so like this, so m, L and t are involved. Similarly, so volume is area into length, something like that. So area is L into L square. So now here this the expression for a derived quantity. So if you derive an expression for these quantities, the which are known as the derived quantities. So in that if you write an expression for these derived quantities in terms of the primary quantities like mass, length and time, so then it is known as the dimensions of a physical quantity. For example, if you want discharge, say like area into velocity. So what is area? L into L, so L square. So what is velocity? It is L by t. So therefore it is expressed as L cube by t, or L cube t minus 1. So m to the power of 0, L cube t minus 1. So when it is expressed in terms of MLT system, for then this particular this is known as the dimensions of discharge. Similarly, force is known as mass into acceleration. So mass is m, acceleration is L by meter per second square, that is L by t square. So it is expressed as MLT minus 2. So before we go for Rayleigh's method or Beckham's by method, so we should know the dimensions of various physical quantities, like in a geometric physical quantities are length, so expressed as L, area L into L square, volume, that is meter cube, that is L cube, slope, it is so say it is one horizontal, one vertical, so m to the power of 0 is a dimensionless term, m to the power of 0, L to the power of 0, T to the power of 0. Similarly, angle is also m to the power of 0, L to the power of 0, T to the, so it is expressed in radians or degrees. Similarly, we have the physical quantity related to kinematic, so that is time, so expressed as t. So velocity is length by time, so lt minus 1. So angular velocity again radians per second, so therefore it is 1 by t, that is t minus 1. Similarly, angular acceleration is radian per second square, so therefore it is t minus 2. Acceleration is now meter per second square, so therefore lt minus 2. Acceleration due to gravity again is meter per second square, so it is Lt minus 2. And discharge, you know that it is volume by time, so volume is L cube and T minus 1. So discharge per unit width, so it is Q divided by B, so that is meter cube per second, per meter is meter square per second, so it is L square by T. Okay, so kinematic, so it is mu by rho, so it is always expressed as meter square per second, so therefore L square per second. Either you should know the units, or you can know the definitions from that, from the definition. So rho is mu by so there is a kinematic viscosity, nu is mu by rho, and from there you can derive the dimensions of kinematic viscosity. So similarly, the terms related to the dynamic is the mass, that is m, force is mass into acceleration, so m lt minus 2. So weight is a force unit, again it is m lt minus 2. Mass density is mass by volume, so m l minus 3. Specific weight is nothing but weight by volume, so Newton. So Newton is force is m lt minus 2. Then specific weight, okay, so that is Newton per meter cube, so here divided by L cube, so that gives ml minus 2 T minus 2. Specific gravity is no dimensions, so it is m to the power of 0, no units, m to the power of 0, L to the power of 0, T to the power of 0. Pressure intensity is force by area, so if you take force and divide by area, so you will get ml minus 1 T minus 2. Similarly, shear stress, you know that it is again force by area, so same units. So dynamic viscosity mu is Newton second per meter square. Okay, so Newton second per meter square. So you can get the units. That is so m l minus 1 T minus 1. Surface tension is force per unit length. So again you will get mt minus 2. So modulus of elasticity is again a stress unit. So it is whatever you wrote for stress has to be written here, or for pressure. So then the compressibility is 1 by E, so again meter square per Newton, you can write it. So the momentum is nothing but mass into velocity, mlt minus 1. So work done or energy is force into distance, so force multiplied by distance. So write the dimensions for force and multiply by the distance, so ml square T minus 2. Similarly, the torque is nothing but force into distance, so which is same as work, so it is ml square T minus 2. Similarly, power is work by time, so that gives ml square T minus 3. So like this you should be able to write the dimensions of all the quantities that are involved. Now coming, as I told you earlier, that dimensional homogeneity, a equation is said to be dimensionally homogeneous if the dimensions of the terms on the left hand side is equal to dimensions of the term on the right hand side. For example, Q is equal to 2 by 3 CD root 2 G LH to the power of 3 by 2. So you know that Q is discharge, which is L cube by T, whereas so this doesn't have any unit. So G is meter per second square, so LT minus 2, so because of square root raised to the power of half L, and H is again L, so which is head, so it is L to the power of 3 by 2. So when you solve this, so you get L cube by T, and left hand side is also L cube. So hence this equation is dimensionally homogeneous. So that means the dimensions of the terms on both the sides of the equations are same, and hence it is said to be dimensionally homogeneous. So here, what is the advantage of having a dimensional homogeneous? It is independent of the unit chosen for the measurement. If it is a dimensional homogeneous, then you can you use it without any modification with either system of units. You can use it in MK system or SI system, or any system of units. In addition to this, there are other equations in hydraulics which are dimensionally non-homogeneous. For example, Chassis equation, or V is equal to C root RS, or Manning's equation, which is V is equal to 1 by N R to the power of 2 by 3 to the power of half. So you know that V is LT minus 1. So here it is R. As you, this doesn't have any dimension, so R is that is L, that is area divided by perimeter, so the units is meter, so L to the power of 2 by 3. So you can see that the dimensions of the left hand side is not equal to dimensions of the right hand side. So therefore this particular equations have to be used only in SI or metric system of units, with V in meter per second and R in meters. So other examples of dimensional non-homogeneous equations such as this equation, that is V is equal to C root RS. So we also discussed about specific speed. So N is equal to N root P H to the power of 5 by 4. N has to be in RPM, and P has to be in kilowatts, and H has to be in meters. Okay, so these are these are some empirical equations which are dimensionally non-homogeneous. Hence, that particular these physical quantities have to be expressed in a particular unit. So the first method of dimensional analysis is Rayleigh's method. Again, here in this method, a functional relationship of some variables are expressed in the form of an exponential equation, which must be a dimensionally homogeneous. For example, if x is a function of some variables x1, x2, x3 to xn, so then x can be written as a function of x1, x2, x3 to xn. But in this equation, we know as x is known as a dependent variable, whereas x1, x2, x3 are known as independent variables. So what is a dependent variable? A dependent variable is one about which the information is sought, or for which the information is required, whereas the independent variables are those which govern the variation of the dependent variables. So therefore, now equation 1 can be expressed as in the form of an exponential equation, which is written as x is equal to c some constant to x1 to the power of a, x2 to the power of b, x3 to the power of c, to so on to xn to the power of n. So where c is a dimensionless constant. Here exponents a, b, c to n are evaluated on the basis that it is a dimensionally homogeneous equations. So after making it as dimensionally homogeneous, so substitute the dimensions of each of the quantities on left hand side and right hand side, and then since it is dimensionally homogeneous, you can equate you can work out the powers a, b, c by forming or by grouping together the variables with the like powers. Okay, so this will be told very clearly in the problems. So how to find out a, b and c, and then rearranging to form an equation. Now this is the method where we have to use the Rayleigh's method, where the resistance R to the motion of a sphere of diameter d moving with the uniform velocity v through a fluid having density rho and viscosity mu. So maybe expressed as rho R equals rho d square v square, a function of mu by rho v d. So this is one dimensionless term. So R by rho d square v square is another dimensionless term. So now according to Rayleigh's method, so now it is given that so R is a dependent variable, whereas mu, rho, v, d are independent variables. So therefore R is a function of mu, rho, v and d. By this method, by Rayleigh's method, we can write as R as an exponential equation. So therefore it is written as some c or k as a constant. So mu to the power of a, rho to the power of b, v to the power of c, d to the power of small d. So therefore now the next step is to substitute the dimensions. You know that resistance is nothing but the force. So force is mass into acceleration. So m L T minus 2. So this is a dimensionless term. So m to the power of 0, L to the power of 0, T to the power of 0. So mu is the dynamic viscosity, which is expressed as ml minus 1 T minus 1 to the power of a, where density is ml minus 3, this mass by volume. So to the power of p, velocity is lt minus 1 and the diameter is L. So now the next step is to you raise it to the you work out the indices which is raised to the for the m, L and T. So therefore here we have m to the power of a and m to the power of a, which can be written as m a plus to the raised to the power of a plus b. Similarly for L we have minus a minus 3b minus c plus d. So that's how it is written. So again for t we have t minus 1 into a and here minus 1 into c. So it is written as t to the power of minus a minus c. So this is the next step that what we do. So till here we have discussed. Now for dimensionally homogeneous we can equate since it's a dimensionally homogeneous equation we can equate the exponents of m, l and t. So for m it is a plus b, here it is okay, here so m, yeah, so here it is m to the power of 1, l to the power of 1, t minus 2. So a plus b is equal to 1. So therefore you can express in terms of a. So now expressing in terms of a, so here b equals 1 minus a. So now again for t you can take as minus a minus c is equal to minus 2. So therefore c can be written as that is 2 minus a. So similarly for L it is minus 1, L power is 1, so 1 should be equal to minus a minus 3b plus c plus d. So therefore now you can say that d will be equal to 1 plus a plus 3b minus c. Now you know that you keep a as it is. For b you can substitute as 1 minus a. For c you can substitute as 2 minus a. So now simplifying this, so 3 minus 2 is okay, so 1, so 1 plus 1 is 2. So this the minus 3a plus 2a is okay, minus 3a and plus a is minus 2a minus 2a plus a is minus a, so it becomes 2 minus a. So now since you know the power, so you can substitute here. So r is equal to k mu to the power of a. Rho is written as 1 minus a because b is written as 1 minus a. Similarly c is written as 2 minus a and d is written as 2 minus a. So now you can again write it as say here, so k, this rho to the power, so rho is taken out. Similarly v square is taken out and here d square is taken out. So what remains here is mu. So here it is rho to the power of minus a, it comes down, so rho. So again v to the power of minus a, so v comes to the denominator, so d to the power of minus a, so raise it to the power, so this is like power. So now we have arranged the dimensionless terms with the like powers, so therefore this becomes one of the dimensionless number. So another is that, so we have, so now we can write it as like the equation which can be got like r as can be expressed as rho d square v square, that is r by rho d square v square is one of the dimensional term. So similarly the function of mu by rho bd is another dimensionless term. So this is how we get the expression by Rayleigh's method. The second problem is that for a laminar flow in a pipe, the drop in the pressure dou P is a function of pipe length L, its diameter D, mean velocity of flow V, dynamic viscosity mu. So you have to use Rayleigh's method and develop an expression for the pressure drop. So now you know that the pressure drop is a function of length, diameter, velocity and dynamic viscosity. So therefore now you can write it as that, you can raise it to the power. So the dou P can be written as k L to the power of a, d to the power of b, b to the power of c and mu to the power of d. So now putting the dimensions, so for pressure it is force by area, so that you know force is mlt minus 2 divided by L square, that comes ml minus 1t minus 2. So this m to the power of 0, L to the power of t to the power of 0. So here L is written as L, so d again is expressed in terms of L. Similarly velocity is expressed in terms of meter per second, Lt minus 1. So mu is, you know that it is ml minus 1t minus 1 raised to the power of so like A, B, C and D. So now what you have to do is that ml minus 1 t minus 2 is written as it is. So m is here m to the power of d. Similarly L has raised to the power of a plus b plus c minus d. Okay, and t is written as t to the power of minus c and minus d. Okay, so this is how you write. So now making it the dimensionally homogeneous equation. Now we can write as d is equal to 1. Again equate the powers, so we can write here here we can get for m d is equal to 1. Similarly minus 2 is equal to minus c minus d, so c can be written as 2 minus d. So since d is 1, so we get c is equal to 1. Similarly for L we have minus 1, you equate the powers, so simply get the value of b, which is minus 1 minus a minus b plus d. So we got as minus 1 minus a. So you can put the powers here, here. So it is dou p should be equal to k L to the power of a d to the power of b. So b is here minus 1 minus a, and b to the power of c is 1, and again mu to the power of d, so d is 1. So therefore we can write it as here k, here mu, this is v, and mu v by d to the power of minus 1 can be written as mu v by d. Then other like powers is that L to the power of a and d to the power of minus a, which is written in the denominator as raised to the power of a. So this can be expressed now, taking out the dimensionless constant and writing as the equation as, so dou p, because this is one of the dimensionless term, which is dou p by this term, and L by d is another dimensionless term. So therefore it can be written as dou p equals mu v by d, a function of L by d. So this is how we get. So these two problems were such that here the we have unknowns as a b c d, and there are three equations, so three equations. So therefore you can solve three, but the other quantities should be expressed in terms of either in terms of a or b or c. So whichever is important parameters has to be noted down. So therefore here a because here is the very important parameters, and hence it is all expressed in terms of a. Now the efficiency eta of a fan depends on the density rho, dynamic viscosity mu of the fluid, angular velocity omega, diameter d of the rotor, and discharge q. We have to express efficiency as a function of mu by rho omega d square, q by omega d cube. So now eta is a function of rho, dynamic viscosity mu, and angular velocity omega, diameter d, and discharge q. So by Rayleigh's method we can write it as, because this is the dependent variable and these are independent variables, so it is k times rho to the power of a, mu to the power of b, omega to the power of c, d to the power of d, q to the power of e. So now putting the dimensions, so here it is a dimensionless term, so m to the power of 0, L to the power of 0, t to the power of 0. Similarly this is a dimensionless term, so m to the power of 0, L to the power of 0, and t to the power of 0. So we have density as m L minus 3 to the power of a, mu, you know the dynamic viscosity is m L minus 1 t minus 1 raised to the power of p. Here it is radians per second, so t minus 1 to the power of c, and similarly this is the length term, so power of d, and discharge is nothing but meter cube per second raised to the power of e. So now writing this m here m to the power of a plus b, so this is written L minus 3a, so minus b, then plus d, then plus 3e. Then for t we have t minus b, then here minus c. Similarly we have here minus e, so it is written as t to the power of minus b minus c minus c. So here we can find that a b c d e, there are 5 unknowns but only 3 equations. So hence we have to express these 3 unknowns in terms of the other 2 unknowns which are very important. So we have to identify the 2 unknowns which are very important. So here you can see this equation. So for mu and q, you have to see, for mu it is b and for q it is e. So therefore, so b and e are very important terms. So therefore you have to express a c d in terms of b and e. Okay, so again note that there are 5 unknowns: A, B, C, D and E. There are only 3 equations, okay, in M, L and T. So therefore there are 5 unknowns and 3 equations. So we can express these 3 unknowns in terms of the other 2 unknowns, so which are very important. Which are the 2 important? Here the velocity, here the viscosity mu and discharge are very important. So that's the reason, since mu is raised to the power of b and q is raised to the power of e, so b and e becomes very important. So now you express a, c and d in terms of b and e, so you have to be careful here. So that's what done here. So equating the dimensions for m, l, exponents of m, l and t. So we get 0 equals a plus b. So now we are expressing a, c and d in terms of b and e. So that's what we have done. So a is equal to minus b. Similarly, if you get for exponents for t, so it is 0 is equal to minus b minus c minus e. So therefore we are getting c in terms of b and e. So similarly, we express exponents of L, so we get D in terms of B and E. So we know that 3A plus B minus 3E, but A is written as minus B, so that's how. So minus 3B plus B is minus 2B minus 3. So now we have expressed A, C, D in terms of B and E. So put it back in the equations. So in the expression equations, where that is for efficiency equation as k times rho to the power of a is minus b, mu to the power of b, okay, then omega to the power of c is minus b minus c, d to the power of small d, which is here minus 2b minus 3e, and q to the power of E. So here we have expressed everything in terms of B and E. So this can be written as K times, say, mu. So first like powers are B and E. So we are expressing in terms of like powers. So mu divided by rho omega and d square. So minus 2. So it's d square. So similarly we are expressing in terms of like power E, which is q divided by this is omega and d to the power of minus 3 as dq. So now we got this as one dimensionless term, and this is also another dimensionless. Hence this dimensionless term can be expressed in terms of this dimension and this dimension. So that's why written as a function of mu by rho omega d square and q omega dq. So that is the expression that we require. So another problem is that the resistance R to the motion of a partially submerged body in a water depends upon the density rho, okay, density rho, viscosity mu, length L, velocity v of the body, and acceleration due to gravity. We have to show this, we have to prove this equation. So now we know that resistance is a function of rho, mu, L, V and G. So therefore R is a dependent variable, whereas these are the independent variable. Now expressing R by an exponential equation, that is k rho to the power of a, mu to the power of b, L to the power of c, v to the power of d, g to the power of e. So you can express in any order you want. So now generally if we follow this this order, which is the statement order, so I have written like this. So now we express the dimensions. So this R is nothing but the force, that is m L T minus 2. This is mass by volume, that is okay, mass by ml minus 3. Then this mu is nothing but ml minus 1 t minus 1. So this is already a length term. Here the velocity is lt minus 1, g acceleration due to gravity meter per second square, so lt minus 2. So this can be written as m a plus b, that's all, a plus b. L is minus 3a minus b plus c, then plus d and plus e. Okay, so for t it is t minus b minus d and minus 2e. So now we can say that a, b, c, d, e, there are 5 unknowns, equations are only 3. So we have to express these 3 unknowns in terms of the other 2 unknowns, which are very important. In this case the viscosity is very important, and okay, the term that is here G is very important. So this is a little bit writing it is wrong. So here it is G is very important. Acceleration due to gravity. So G is important. So for G term we have E as the exponent. So therefore, so which is important now? So B is important because mu is involved with B, power B. So this is, and G is involved with E. So therefore we have to express A, C, D in terms of B and E. Now equating the powers for M, L and D. So we have 1 is equal to A plus B. So we are expressing A, okay, in terms of B, which is 1 minus B. Similarly, equating the exponents for T. So minus 2 is equal to minus B minus D minus 2E. So D can be written as 2 minus B, and so we have expressed in terms of B and E. Okay, so then we have for L as C is equal to 1 plus 3A plus B minus D minus E. So we want A in terms of B, so therefore we have expressed the 1 minus B, we have substituted here, so B remains as it is. So instead of D we want 2 minus, because we want to express in terms of B and E, so we have written here. So there similarly E remains as it is, and then simplifying it is 2 minus B minus 2 minus B plus E. So substitute here A as 1 minus B, B as it is, C as 2 minus B plus E, then D as 2 minus B minus 2E, and G to the power of E. So therefore it is written as, so rho to the power of 1 here, so L square, and this is written, and v square is written. So R by rho L square v square is one of the dimensionless term. Similarly we can write for the like powers of B. So this is mu, so there is mu to the power of rho minus B. So the rho comes down here, V to the power of minus B, so V comes here. So then next L to the power of minus B, so that means another term with a like power B is mu by rho VL. So the next term is L. Here we have the like power is E, L to the power of E, G to the power of E, so Lg divided by V to the power of minus 2 becomes V square. So that means R by rho L square V square is a function of mu by rho VL and Lg by V square. Therefore R is equal to rho L square V square, a function of mu by rho VL and Lg by V square. So that was the few problems where one unknown, or maybe the expressing like three unknowns in terms of two unknowns, or we had expressing three unknowns in terms of one unknown. So a few problems were, so when there are more number of unknowns involved, the equations becomes very difficult. So that's the reason why the analysis method can be adopted up to like the maximum up to 5 unknowns, where you can express 3 unknowns in terms of other 2 unknowns which are very important. But when it goes on increasing, so the number of unknowns goes on increasing, it is very difficult to solve by analysis method. Therefore we can go for another method which is known as the Buckingham's pi method. Here, before we go for the problems, we should know that what is Buckingham's pi theorem. Here in Buckingham's pi theorem, it states that if there are n-dimensional variables which are involved in a phenomenon and can be described by m fundamental quantities or dimensions and should be related to the dimensionally homogeneous equation, then the relationship among n quantities can be always expressed in terms of n minus exactly n minus m dimensionless or independent pi terms. So therefore, if there are n quantities with n physical quantities involved and which are described by m fundamental dimensions and they are related by dimensional homogeneous equation, then there can be a relationship which can be established between these n quantities by exactly n minus m dimensionless or independent pi terms. Now here in this case, if suppose x1 is a function of x2, x3 to xn, so here x1 is known as a dependent variable, whereas x2, x3, xn are known as independent variables. So you know that a dependent variable is the one for which the information is required, and whereas x2, x3, xn are the independent variables which govern the variations of the dependent variables. So you can write these equations as there is no like exponential term here, so therefore we can write it as a function. Is there something like f1 is f1 of x1, x2, x3, xn equal to 0. Then equation 2 is dimensionally homogeneous, can be made as a dimensionally homogeneous equation which contains n variables, and if they are expressed by the m fundamental dimensions, then according to Buckham's pi theorem, it can be written as the equation 2 can be written in terms of dimensionless groups, which are known as pi terms. So it is a function of say pi 1 term, pi 2 term, pi 3 term to pi n minus m terms. So that's why I told you that there are n minus m exactly dimensionless terms. So therefore the terms, the number of pi terms will be equal to n minus m. So each of the pi terms can be always expressed in terms of the, the dependent variable and the independent variable. So they are written as x to the power of a1, x3 to the power of b1, x4 to the power of c1. So this term is known as the dependent variable. Similarly, then again we write pi2 as x2 to the power of a2, x3 to the power of b2, x4 to the power of c2. Okay, so these terms are getting repeated in each of the pi terms, so therefore they are called as the repeating variables. So x4 to the power of c2 like this, x2 to the power of a3, x3 to the power of b3, x4 to the power of c3, x6 like this. So we try to work out each of the pi terms and then substitute in this equation. So now each equation is solved by principle of dimensional homogeneities, and the values of a1, b1, c1 or a2, b2, c2 are is got, and again substitute in the pi 1, pi 2 or pi so and so on terms, and this, and then finally the equations is obtained. Finally the pi 1 term, pi 2 and pi 3 terms so on is substituted in this equation and the expression is got. So now I can again show you how to solve this the values of the indices or the that is a1, b1, c1 or a2, b2, c2, and how to get the pi 1, pi 2, pi 3 terms. Few points should be noted in the Buckham's pi method, that we have to list the n physical quantities in the phenomenon, and we have to note their dimensions, how many fundamental dimensions are there, and then generally it will be equal to 3 because all MLT system will be involved, M, L and T will be involved, so therefore dimensionless pi terms will be n minus m. So each pi terms will consist of m plus 1. So if there are 3, m is equal to 3, then each pi term will consist of 4 variables, and in that pi term, the number of I told you that there are repeating variables in each of the pi terms, and these repeating variables will be always equal to m, and therefore the extra, that m plus 1, another variable, has to be the non-repeating variable that doesn't get repeated in each of the pi terms. And then as far as possible, the dependent variable should not be taken as the repeating variable. And how to select that repeating variable? The repeating variables are those which gets repeated in each of the pi terms. So these should be chosen in such a way that one should be a geometric property, other should be a flow property, and third variable should be a fluid property. Okay, for example, rho Vd, rho Vl. Rho is a fluid property, V is a flow property, and D is a length property. So like this, you can have various combinations where the repeating variable is selected such that one should be a geometric, that is L, the flow property like V, acceleration due to gravity, like that, and third variable like mu, rho, something like that, anything connected with the fluid properties. The repeating variables, those selected, should not form itself a dimensionless group, and no two repeating variables should have the same dimensions. If you cannot select the repeating variables which have the same, no two repeating variables should have the same dimensions. That means you cannot select two flow properties or two length properties like that. So coming to the problems, so we have we have to show by Buckham's pi method the resistance R to the motion of a sphere of diameter by Rayleigh's method. This method will be so easy to solve, where not much complications are involved. So here you have to show that R is rho d square v square function of mu rho vd. So now R is a function of here rho, that is okay, rho v d and mu. So now you can, in the equation you observe that it is rho Vd. So rho, this is a fluid property, flow property, length property. So therefore this can be selected as a repeating variables. So there are how many variables now involved? So 1, 2, 3, 4, 5. So including dependent variable and independent variable, total 5. We have fundamental dimensions as 3 because m in mass by volume, m, l, in velocity there is time, in mu there is time. So all the three the physical quantities are involved, like MLT. So therefore number of pi terms is n minus m, so 5 minus 3 is 2, so therefore there should be 2 pi terms. So how many variables are there in each of the pi terms? It is always m plus 1, so 3 plus 1, that is 4. So number of repeating variables has to be 3. So one has to be fluid property, so we can take rho. Another has to be flow property, we should take v. Another has to be a geometric property, so it is d. So therefore, so there are 2 pi terms now. So how it is written? So it is always so these are the repeating, rho v d is repeating, so it gets repeated in each of the pi terms. So another here, as far as possible, this term has to be dependent variable, so we wrote. So what is remaining? So only mu is remaining, so mu comes here as a non-repeating variable. So therefore it is written as rho to the power of a1, v to the power of b1, d to the power of c1 r. And similarly this should not be raised to the power. So pi 2 is written as rho to the power of a2, v to the power of b2, d to the power of c2 mu. Now writing the dimensions, so m to the power of 0, l to the power of 0, t to the power of 0. So rho, you know, it is m l minus 3 to the power of a1. So velocity is lt minus 1 to the power of p1, and diameter is say L to the power of C1, and resistance is the force, that is mass into acceleration, mLt minus 2. So now writing this as MA1 plus 1. Similarly for L, minus 3A1 plus B1 plus C1 plus 1. Similarly for T, it is T minus B1 and minus 2. So making it dimensionally homogeneous, so equating the powers, so we write a1 plus 1 is equal to 0, so therefore a1 will be minus 1. So here we get the values of the exponents or the powers. So similarly we can go for next here for t, which is minus b minus 2 is equal to 0, so b1 will be equal to minus 2. Similarly now we know the values of a1 and b1, so you can equate the powers for L. So minus 0 is equal to minus 3a1 plus b1 plus c1 plus 1. So you can substitute the value of a1 as minus 1, substitute the value of b1 as minus 2, and solve for c1, which comes to minus 2. So now you can substitute the values of a1, b1, c1 in this equation. It is rho to the power of minus 1, v to the power of minus 2, d to the power of minus 2 r. So that becomes r by, so this is one of the dimensionless term. So we have grouped now into a dimensionless term as r by rho v square d square. Like this we can write for a pi 2 term. So again pi 2 term is written, so again the same dimension raised to the power of a2, b2, c2. So now here m a2 plus 1, similarly l minus 3a2 plus b2 plus c2 minus 1, similarly t minus b2 minus 1. So now equating the powers for m, a2 plus 1 is 0, so a2 is minus 1. Similarly for t, minus b2 minus 1 is 0, so b2 will be minus 1. Similarly minus 3a2 plus b2 plus c2 minus 1 is 0 for L. So therefore you can, by knowing the values of a2, knowing the values of b2, you can solve for c2. So now substitute the values of a1, a2, b2, c2 in, so rho to the power of a2, b to the power of b2, d to the power of c2. So we get mu by rho bd. So that's how we know that the pi 1 is also a function of pi 2. So substitute the values of pi 1 here and rearrange, and we get the required equation. So therefore Buckham's pi method becomes so easy when you compare to Rayleigh's method. The same problem we have solved by Rayleigh's method, and the same problem is also solved by Buckham's pi method. This problem also was solved. So here in this case, so dou p is a function of here the pressure drop is a function of length, diameter, velocity and mu. So number of variables involved is 1 2 3 4 5. Number of fundamental dimensions, because in this case we have m, l and t, so therefore m is equal to 3. So therefore the number of pi terms is n minus m, so that is 2. So number of variables in each of the pi terms is m plus 1, so therefore 3 plus 1 is 4. So number of repeating variables is equal to m, so therefore 3. So we have to select correctly. One is the fluid property, other is the flow property and the geometric property. So here in this case, since rho is not there, mu is there, so this can be taken as the 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 fluid property, this is the flow property, and d can be taken as the length property. So mu, v and d can be expressed, and non-repeating variables can be the other two, okay, which is dou p and l. So pi 1 can be written as mu to the power of a1, b to the power of b1, d to the power of c1 dou p, and pi 2 can be written as mu to the power of a2, b to the power of b2 and d to the power of c2 l. So substituting, taking pi 1 term, you substituting the dimensions m to the power of 0, l to the power of 0, t to the power of 0 is, here mu is m l minus 1 t minus 1 to the power of a1, velocity is lt minus 1 to the power of b1, and d is l to the power of c1, and the pressure is force by area, which is m l minus 1 t minus 2. So rearranging this, m to the power of a1 plus 1, l minus a1 plus b1 plus c1 minus 1, t minus a1 minus b1 minus 2. So now equating the powers of m, so a1 plus 1 is 0, so therefore a1 is minus 1. Equating the powers of t, we get minus a1 minus b1 minus 2 should be equal to 0. So therefore we know the value of a1, which is minus 1, so therefore we can substitute and get b1 as minus 1. We equate the powers for l and substitute the values of a1 and b1, so we'll get c1 as 1. So therefore you can substitute a1, b1, c1 in this equation. So it is mu to the power of a1, which is minus 1, b to the power of b1, which is minus 1, and d to the power of c1, d to the power of c1, that is 1. So we get dou p d by mu into v. So this is the equation for the pi 1 term. Similarly, for the pi 2 terms, you can raise it to the power of a2, b2, c2, and the non-repeating variable is l. So therefore now again writing m to the power of a2, that's all, l to the power of minus a2 plus b2 plus c2 plus 1, t to the power of minus a2 and minus b2. So equating the powers of m, l and t, we can work out the values of a2, b2 and c2. So it comes to 0, b2 is 0, c2 is minus 1. So you know that the ratio of two length terms is one of the pi terms. You could have written directly, but anyway we have solved. So that's the reason why we should get L by D, and that's the reason why the power of A2, B2 is 0. So for D we got as C2 as minus 1, so therefore it is L by T. So now pi 1 is a function of pi 2, so therefore substituting pi 1 term here, pi 2 term here, and rearranging to get the required equation. This problem where in Rayleigh's method was rightly because there were 5 unknowns and 3 equations, equations. So therefore we expressed 3 unknowns in terms of other 2 unknowns. But that problem doesn't arise here because the number of variables here is 6. So 1, 2, 3, 4, 5, 6. Number of fundamental dimensions are 3. So 6, my number of pi terms will be 6, n minus m. So 6 minus 3 is equal to 3. So there in the two problems we got pi terms as 2. Now we get, because it is number of variables increases, number of pi terms also increases. So therefore it is 3 here. So number of variables in each of the pi terms is m plus 1. So therefore 3 plus 1 is 4. So you have to select where number of repeating variables, which is equal to m. So in this case here it is very clear that rho is a fluid property. Here this is a flow property omega, and d is a length. So that by taking rho, omega and d is the repeating variables, the other 3 will be remaining. So that will be eta, that is dependent variable, and mu and q can be taken as the non-repeating variables. Now writing here, say this rho, omega, d are the repeating variables which occurs in all the three pi terms, and similarly that has to be raised to the powers here. So like a1, b1, c1, a2, b2, c2, a3, b3, c3, and all other the remaining three will become the non-repeating variables. So therefore for the first pi term you should always write the dependent variable. So therefore since the efficiency was the dependent variable, we write here. The other two terms remaining will be mu and q. Okay, so for the pi 1 term we write it as like this is m to the power of 0, l to the power of 0, t to the power of 0. Density is ml minus 3 to the power of a1. Here this is radians per second, so t minus 1 to the power of b1. L is l to the power of c1. Similarly efficiency is output by input, so therefore it is dimensionless, m to the power of 0, l to the power of 0, t to the power of 0. So we can write it as m to the power of a1, so plus 0, L is minus 3a1 plus c1, that's all, and t to the power of minus b1. Okay, so now equating the powers of a1, so a1 is 0, so similarly equating the power of b1, so b1 is 0, and similarly equating the powers for L, minus 3a1 plus c1 should be equal to 0, but c1 is equal to 3a1 but is already 0, so therefore c1 is also 0. So therefore now since this is a dimensionless term, so this has to be zeros. So it is rho to the power of 0, omega to the power of 0, d to the power of 0. So therefore pi 1 you could have written directly because efficiency is already a dimensionless. However, we have proved by this method that pi 1 is equal to one of the dimensionless term, which is the efficiency. Next term is pi 2 is equal to rho to the power of a2, omega to the power of p2, d to the power of c2, mu. So putting the dimensions m to the power m l minus 3 to the power of a2, t to the power of minus 1 to the power of p2, l to the power of c2, m l minus 1, t minus 1. So now we can write it as m a2 plus 1, l minus 3a2 plus c2 minus 1, t minus b2 and minus 1. So equating the powers of a2 for m, a2 plus 1 is 0, so a2 is minus 1. Similarly equating the power minus b2 minus 1 is equal to 0, so b2 is minus 1. And similarly equating minus for L, minus 3a2 plus c2 minus 1 is equal to 0. So now c2 is 3a2 plus 1, so substituting the value of a2 as minus 1, we get minus 2. So substitute the values of a2, b2, c2 in this equation, so we get pi 2, that is rho to the power of minus 1, omega to the power of minus 1, d to the power of minus 2. Okay, mu. So it is mu rho omega. So it should be omega. So not. Okay, so it is omega minus 1. So therefore it is. This is not there. So it is. Okay, rho omega here should have been d square. So make this correction. So it is. Okay. So next term is rho to the power of a3, omega to the power of b3, d to the power of c3q. So ml minus 3a3, here t minus 1 b3, l to the power of c3, here it is meter cube per second. So now ma3, that's all, l minus 3a3 plus c3 plus 3. Then for t minus b3 minus 1. So equating the power for m, so a3 has to be 0, and for b3 minus b3 minus 1 is equal to 0, so b3 is minus 1, and similarly minus 3 a3 plus c3 plus 3 should be equal to 0, so that has to be, so therefore since a3 is 0, so it is minus 3. So now substitute the values of a3, p3, c3 in this equation. It is rho to the power of a3, that is 0, omega to the power of minus 1, and d to the power of minus 3. So it is q by omega dq. So the equation is, now substitute the pi 1 is a function of pi 2 and pi 3. Substitute the value of pi 1 as this is nothing but omega d square. For example, this is omega d square. Okay, so make this correction, so this is not there, so that is the required equation that we got. So the resistance R to the motion of partially submerged body in water depends on density, viscosity, length, velocity, and acceleration due to gravity. So R is a function of rho, L, V, mu, G. So how many variables are there? 1, 2, 3, 4, 5, 6. Number of fundamental dimensions are 3. So n minus m is 3. So number of pi terms has to be 3. So each number of variables in each pi term is always 4. Out of that, 3 will be the repeating variables. So how will be the repeating variable selected? So for example here rho VL. So fluid property, flow property and length property. So what are the remaining terms? So since we have selected rho VL, so this R will be a non-repeating, okay, mu will be a non-repeating and G will be a non-repeating. So that's how we write pi 1 terms. So rho to the power of a, so these are the repeating variables rho VL and this is the non-repeating variable. So non-repeating variables. So taking pi 1 term now. So rho is ml minus 3. So velocity is lt minus 1. L. So resistance is 4. So mlt minus 2. So raise it to the powers now m a1 plus 1. So L is minus 3a1 plus b1 plus c1 plus 1. Similarly for t it is minus b1 minus 2. Okay, now equating the powers of m, so a1 plus 1 is 0, so a1 is minus 1. Similarly equating the powers for t, it is minus b1 minus 2 is equal to 0, so b1 is minus 2. Similarly equating the powers for l, that is minus 3a1 plus b1 plus c1 plus 1 is equal to 0, so we want c1 now. So c1 is written as 3a1 minus b1 minus 1. So similarly substitute the values of a1 as minus 1, b1 as minus 2, we'll get c1 is equal to minus 2. So now rho to the power of, substitute here in pi 1 term, rho to the power of a1 is minus 1, b to the power of b1 is minus 2, l to the power of c1, that is c1 is minus 2 r. So that gives r by rho v square l square. Now for again pi 2 we have this non-repeating as mu, so we substitute as m l minus 1 t minus 1. Similarly we know the dimensions for rho v l. So now we equate here, so it's making dimensionally homogeneous. Now m to the power of a2, here there is 1 plus 1, l minus 3a2 plus b2 plus c2 minus 1. Similarly t minus b2 and minus 1. So similarly equating the powers for m, a2 plus 1 is equal to 0, so a2 is minus 1. Similarly for t, it is minus b2 minus 1 is 0, so b2 is minus 1. And similarly for l, minus 3a2 plus b2 plus c2 minus 1 is equal to 0, so we get c2 as minus 1. So we get, so rho to the power of minus 1, v to the power of minus 1, l to the power of minus 1 mu. So that is the another pi term, pi 2 term, which is mu by rho vl. The third equation is for non-repeating variable is g, so meter per second square. So again express a m to the power of a3, l minus 3a3 plus b3 plus c3 plus 1 for t minus b3 and minus 2. So similarly equating the powers for m, so a3 will be 0. Similarly equating power for t, that is minus b3 minus 2 is equal to 0, so b3 is minus 2. Similarly equating the powers for l, so minus 3a3 plus b3 plus c3 plus 1 should be equal to 0. So therefore you can express c3 like this and substitute the values of a3 and b3, so we get c3 as 1. Substitute the values of a3, b3, c3 here. So rho to the power of a3, that is 0, rho to the power of 0, v to the power of minus 2, l to the power of 1. So we'll get gl by v square. So you know that pi 1 is function of pi 2 and pi 3. So substitute the values of pi 1, pi 2, pi 3 and rearrange the equation. Using Buckham's pi theorem, we have to show that the velocity through a circular orifice is given by v is equal to root 2 gh function of mu by rho vh dh here. So now v is the equation given where we want the information about this velocity. So therefore that becomes a dependent variable. So though here rho vh, the v is the flow property, we cannot take it as a repeating variable. So I have to be very careful because dependent variable cannot be taken as a repeating variable. So v is a function of your like, okay, so here h, that is given h d then mu rho g. Okay, so number of variables are 6, number of fundamental dimensions are 3, number of pi terms is 3, number of variables in each pi term should be equal to m plus 1, so 4, number of repeating variables should be equal to m, which is 3. So therefore here you have to be very careful in taking the repeating variables. V is a dependent variable and should not be selected as a repeating variables. So repeating variable can be here like a combination like row. Here we have since we cannot take V as the flow property, the other flow property remaining is G. So that's the reason why the flow property is taken as G, whereas fluid property is row and geometric property is H. So this combination where V cannot be taken. So that is what. So non-repeating variable has to be now V, G and H. So that's how we solve the problems like pi1, which is written as a here. So it comes as a dependent variable, so hence a non-repeating variable. It cannot be put in the repeating variables. So other two will be non-repeating, will be mu and d. So working out now pi1 term. So rho we know ml minus 3, g is meter per second square, so lt minus 2, h is head, that is l, and velocity is lt minus 1. So equating, so m is a1 for L minus 3a1 plus b1 plus c1 plus 1. For t it is minus 2b1 minus 1. So equating the powers for a1, so it will be 0. So for equating the powers for, so minus for t minus 2b1 minus 1 should be equal to 0. So b1 will be minus half. Similarly, equating the powers for L, we have minus 3a1 plus b1 plus c1 plus 1 should be equal to 0. Now working out the value for c1, so substitute the values of a1 and b1 will get minus half. So therefore we'll get pi 1 as rho to the power of a1, which is 0, g to the power of half, h to the power of half, b. So therefore v by root g h is the pi 1 term. Next, go for the pi 2 terms with a non-repeating variable as mu, so ml minus t minus 1. So now we're rearranging m to the power of a2 plus 1, l minus 3a2 plus b2 plus c2 minus 1, t is to the power of minus 2b2 minus 1. So now we know that a2 plus 1 is equal to 0, so a2 is minus 1. So again equating the powers for t, minus 2b2 minus 1 is 0, so b2 is minus half. Similarly for L, it is minus 3a2 plus b2 plus c2 minus 1 should be equal to 0. So that's why we rearrange for c2 and substitute the values of a2 and b2, we get minus 3 by 2. So that's how we write, substitute the values of a2, b2, c2 in pi 2 term, which is rho to the power of minus 1, g to the power of half, h to the power of minus 3 by 2 mu. So therefore we'll get pi 2 as this term. So mu by rho, g to the power of half, h to the power of 3 by 2. So it is obvious that h is a linear term, d is a, so you have to get d by h. So a3 has to be 0 and b3 has to be 0. So substituting the dimensions of each of the terms. So here when arranging for the exponents for m, l and t, m to the power of a3, l is minus 3a3 plus b3 plus c3 plus 1 and t is here minus 2b3. So equating the powers for a3, so it has to be 0. Equating the powers for t, it has to be 0 like this, so that's why it is 0, and this has to be minus 1 because it should be a ratio, which is a dimensionless term. So therefore equating the power for L, that is minus 3a3 plus b3 plus c3 plus 1, okay, should be equal to 0. So since a3 is 0, b3 is 0, c3 should be, okay, so here c3 should be minus 1. So it is pi 3 should be d by h. So we want in the form of something like mu by rho vh, the pi 2 term. So therefore what is done is that pi 2 can be written as, so we just so since pi 1 can be here, okay, pi 2 has to be multiplied by the terms like v by, we got v by root j, reciprocal root gh by v, then multiply by this another pi term, so we get mu by rho vh. And we got pi 1 term as v by root j. You can introduce it's because it's already a constant, so if you introduce a constant, it doesn't the dimension, it remains still a dimensionless term. So therefore pi 1 can be written as v by root 2 gh. Now pi 1 is v by root 2 gh, pi 2 is mu by rho vh, because we rearranged this term. So this term is multiplied by another pi term to get this term. So this rearrangement has to be done and then substitute here. So we'll get the equation in the required form. Now it is given that rate of discharge Q is dependent upon the mass density rho, specific pump speed n, diameter of the impeller d, pressure p, viscosity flow. You have to show this. So now if you see these equations, number of variables are involved, so which should not be taken. So this statement becomes very important. So here then you have to rearrange for these equations. So Q is a function of, we have to write it as rho n d p and viscosity. So like this term g, h, nu, this all should not be taken inside. So this statement becomes, seeing this statement, we have to write this equation. So number of variables now is 6, number of fundamental dimensions are 3. So therefore n minus m, 6 minus 3 is 3. So there are 3 dimensions. So q by nd cube is one pi term, this is pi 2 term, this should be pi 3 term. So therefore there should be 3 pi terms. So now how to look find out so rho nd is involved here. So fluid property is rho, n is the flow property, whereas geometric property is d. So therefore we write, so dependent variable is q, so therefore it should not be taken as the repeating variable, so it is a non-repeating variable. Another pressure and mu is a non-repeating variable. Now in the similar procedure, writing for pi 1 term, so rho is, you know that it is ml minus 3, n is nothing but rpm per minute, so t minus 1, d is l, discharge is meter cube per second, so it is l to the power of a1. Okay, L to m to the power of a1, so there is no other m term. So L to minus 3a1 plus c1 plus 3. Similarly for t minus b1 minus 1. So equating the powers, so a1 will be 0. Equating the power for t, the minus b1 minus 1 is equal to 0, so b1 is minus 1. Equating the powers for L, minus 3a1 plus c1 plus 3 should be equal to 0, so c1 is minus 3. So we get pi 1 as q by ndq. Next, coming to the second pi term, that is pi 2. So we non-repeating variable is pressure. Pressure is force by area, where m l minus 1 t minus 2. So m to the power of a2 here plus 1, l to the power of minus 3a2 plus c2 minus 1, t to the power of minus b2 minus 2. So equating the powers for m, so a2 will be minus 1. Equating the power for t, so b2 will be minus 2. Equating the power for L, so we can put the value of a2, so we'll get c2 as minus 2. Substitute the values of a2, b2, c2 in this equation, so we'll get p by rho n square d square. Again, the non-repeating variable for the pi 3 is mu. The repeating variables are rho and d. So for mu, you know that it is m l minus 1 t minus 1, and then it is m to the power of a3 plus 1 here, l to the power of minus 3a3 plus c3 minus 1. Then for t it is minus b3 minus 1. So equating the powers of m, a3 plus 1 is 0, so a3 is minus 1. Equating the power for t, minus b3 minus 1 is 0, so b3 is minus 1. Equating the powers for L, so minus 3a3 plus c3 minus 1 is 0, so therefore c3, substitute the value of a3, will get minus 2. Substitute the values of a3, b3, c3 here, so we get mu by rho n t square. Now we know that pi 1 is a function of pi 2 and pi 3, so we can substitute here. So here what is we want in this required form, so but pressure is nothing but omega into h or rho gh, so therefore rho gh is substituted, so rho and rho gets cancelled out, so you're left with gh by n squared d squared. But here mu by rho can always be written as nu, so it is nu by, so that's why these equations should not be taken as the repeating variables or non-repeating variables, so that later on comes in the expressions. So that statement becomes very important. That's why this problem was taken. So these are a few problems that we were on Riley's method and as well as Buckingham's pi method. I told you what is dimensional analysis. Now you know that it makes use of the dimensions to solve several engineering problems. I also discussed about the dimensional homogeneous equations. So why dimensional homogeneous equation? So dimensions on the left hand side should be equal to dimensions on the right hand side, which we have used in Riley's method as well as in Buckingham's pi method. I also discussed about the various dimensions of many physical quantities, and that were useful for solving many physical phenomenon in fluid mechanics or in hydraulics, which we saw in Rayleigh's method and also in Buckingham's pi method. I also discussed what is the advantage of the Buckingham's pi method, where number of variables starts increasing. So now, but only the pi term starts increasing, but the procedure remains the same. Any number of items can always be solved. Only that is it is that it is little time because number of variables is more, so it is. But we can get any values of items. But in Rayleigh's method, if the number of variables are more than five, say 6 or 7, so solving becomes very difficult. So therefore, we go for Buckham's by method. So they hope these lectures were very interesting for you. You can subscribe to my YouTube channel. This is my YouTube channel link where you can subscribe and view my all the lectures on various civil engineering topics. So you can just click the notification button and you will get the updates whenever I upload new videos on various civil engineering topics. Thank you very much. If there are any queries or any suggestions or any comments on my videos done on various civil engineering topics, you can always contact me. I'm professor department in the Department of Civil Engineering at KLS GIT Belgavi. You can also mail me at r.shreedhar@git.edu. Hope you have gone through my all this many of the videos that I have particularly left on hydraulics and hydraulic machines, and I had also had a few video lectures on hydraulic structures also, and hope you know that this is my 20th video on the civil engineering topic. Hope it will be useful for you, and I have tried my best in convincing the various methods that are involved in dimensional analysis, and my next video will be on model studies, which I will be releasing shortly. Thank you. See, why model studies is necessary. It is necessary to find out in advance how the hydraulic structures, for example, such as the dams or spillways, or maybe an hydraulic machine such as the turbines and pumps would behave when it is actually constructed. So you cannot construct those and then see that how the performance how the performance will be there after it is actually constructed. So that's why what we do is that the engineers have to resort to experimental investigations. So obviously the experiments cannot be conducted on a full size hydraulic structures or on the machines which are proposed to be erected. So therefore it is essential to construct a small scale replica of the structure or the machine, and the tests are performed to obtain the desired informations. So now the small scale replica of the actual structure or the machine is known as the model, while the actual structure or the machine is known as the prototype. Uh, so now this is the prototype of a spillway with its height as h suffix p. Head is a small hp, where the force exerted by the water is afp. So similarly, the velocity in the tailwater may be like vp. So the small scale replica of this is built, which is to some scale, and now this is known as the model, whereas is known as the prototype. So when you build up the model and do the test on it, so these model test results can be utilized to obtain to obtain in advance the performance of the prototype. If this can only you can transfer the results from the model to the prototype if there exists a complete similarity between the model and the prototype. So what are the types of similarities we have? The similarities can be geometric similarity, kinematic similarity, and dynamic similarity. similarity. So geometric similarity is said to exist between the model and the prototype if the ratios of the corresponding linear dimensions in the model and the prototype are same. For example, LM by LP should be equal to HM by HP. Similarly, equal to the head in the model to the head in the prototype should be same. So that scale is known as the linear scale ratio. So that's what I have said here. So linear scale ratios can be any ratio of any length dimensions or width or head or height or something like that. So area scale ratios is always length into breadth or length into width. So therefore LM by LP is known as LR, BM by BP is also LR, so it is LR square. Similarly, the volume can be written as length into width into height. So therefore this is LR, again BM by BP is LR, HM by HP is LR, so it comes as LR cube. So where LR is the linear scale ratio. So now what is kinematic similarity? So kinematic similarity is said to exist between the model and the prototype if the ratios of velocity and acceleration at the corresponding points in the model and the prototype are the same. So for example, if you have the velocity in the model which is measured in the tailwater, the same thing you measure in the prototype at the same corresponding point. So that ratio, if you take velocity in the model to the velocity in the prototype, which is known as the velocity scale ratio. Then dynamic similarity is said to exist between the model and prototype if the ratios of the corresponding forces at the corresponding points the model and prototype are same. So therefore, if you take the ratios of the forces in the model to the force in the prototype at the corresponding points the model and prototype, if they are equal, so then it is known as the dynamic similarity. So if we have some dimensionless number, for example, we have the inertia to the viscous force known as the Reynolds number. So what is inertia force? So inertia force is mass into acceleration, but mass is nothing but density into volume. Acceleration is velocity by time. So here the volume by time is nothing but discharge. So here discharges can be written as area into velocity. So it becomes rho a v square. So a is nothing but L square, okay, and velocity is v, so v square. So it becomes, the inertia force becomes rho L square v square. So what is viscous force? It's nothing but shear stress into area. But shear stress, we know that it is mu dou v by dou y, where so mu is written as it is. So dou v is nothing but a velocity term, y is nothing but the length term, L, and area is L square, so it becomes mu v L. So now Reynolds is nothing but the ratio of inertia force to the viscous force. So rho L square v square by mu VL. So therefore we get VL by nu. This, the ratio rho VL by mu, rho VL by mu, or VL by nu. Nu is a kinematic viscosity, is known as Reynolds number. Now the other number is inertia to the gravity force, where gravity force predominates is the Froude number. So therefore we have inertia force as rho L square v square. But what is gravity force? It's mass into acceleration due to gravity. So mass is nothing but density into volume. So rho L cube g. So if you substitute here to the ratio of the inertia force to the gravity force, we get rho L square v square by rho L cube g, which comes as v square by g into L. So the square root of this ratio is known as Froude's number. So therefore Froude's number is nothing but v by root gl. Now the ratio of inertia force to the pressure force ratio is Ehlers number. So here the inertia force is rho L square v square. What is pressure force? It is nothing but pressure intensity into area, so P into L square. So therefore it is a ratio of inertia force to the pressure force rho L square v square by P L square. So that gives nothing but so L square cancels, so we have V square by P by rho. So v square divided by p by rho. So if you take a square root of this ratio, that gives what is known as an Ehlers number. So it is nothing but v by root of p by rho. So coming to inertia and elasticity forces, so we have inertia force rho L square V square. Elasticity force is nothing but the bulk modulus into area, so which is K into L square. So therefore we have rho L square V square by K L square. So L square cancels, so we get V square by K by rho. The square root of this ratio is known as the Mach number, and root of K by rho is also represented as C, which is velocity of sound in the fluid medium. So V by C or V by root of K by rho is known as Mach number. Then coming to inertia force and surface tension force ratio, which is a Weber number. So where we have the inertia force rho L square V square. So the surface tension force nothing but the surface tension, which is expressed as Newton per meter into length, that gives the surface tension force. Therefore sigma into L. So therefore if you take the ratio rho L square V square by sigma L, so that gives the L cancels out, so it is V square by sigma by rho L. So therefore if you take the square root of this ratio, so that gives what is known as the Weber number. So that is V by root of sigma by rho L is known as the Weber number. So now we have said that for a dynamic similarity between the model and the prototype, the ratio of the corresponding forces at the corresponding points in the model and prototype should be equal. So that means for dynamic similarity, the ratio of corresponding forces acting at the corresponding points in the model and prototype should be equal. But we have studied that the ratio of the forces are the dimensionless number. It means that for dynamic similarity between model and prototype, the dimensional numbers should be same for model and the prototype. So but it is difficult to satisfy all the dimensional numbers which we have discussed in the previous slides for the model and the prototype. Hence the models are designed based on the ratio of the forces which is dominating in the phenomenon. Suppose the viscous force is predominating, then it is Reynolds number is used. Similarly, if the gravity force is predominant, then we are using Froude's number. So therefore the laws on which the models are designed for dynamic similarity are known as the model laws, or also known as the laws of similarity. Now coming to Reynolds model law, now we know that for complete similarity between the model and the prototype, the Reynolds number in the model should be equal to Reynolds number in the prototype if here viscous force predominates in the flow phenomenon. You know that Reynolds number in the model should be equal to Reynolds number in the prototype. What is Reynolds number? It is rho VL by mu. So that is in the model, whereas rho VL by mu in the prototype. So that can be written as rho M VM LM by mu M should be equal to rho P VP LP by mu P. So that is nothing but here velocity in the model to Lm, that is length of the model, by nu m, because mu by rho is written as nu, which is kinematic viscosity. Similarly Vp Lp by nu p. So therefore Vm by Vp is nothing but velocity ratio, Lm by Lp is nothing but Lr, that is linear scale ratio, nu m by nu p is nothing but the nu r. So that should be equal to 1. So this either you can use this formula for solving the problems, or you can use this formula to solve the problems. But finally you should know that for a complete similarity between model and prototype, Reynolds number in the model should be equal to Reynolds number in the prototype, which is the basic equation to solve the problem. So where this Reynolds model law is used, it is used for say for flow of incompressible fluid in closed pipes, or maybe a motion of submarines where completely which is underwater where viscous force predominates, or a motion of the airplanes. So these finds applications in these three cases where we have flow of incompressible fluid in closed pipes, motion of submarines or airplanes, which finds applications of Reynolds model law in the case of flow of incompressible fluid in closed pipes. Now here in this type of problems, you have to identify which is the prototype and which will be the model. So here the pipe of diameter 1.5 is the prototype. So where so diameter of the prototype is given, which is 1.5 meters, is required to transfer. So oil is flowing of specific gravity 0.9, hence its density can be determined. So the specific gravity to density of water, which gives 900 kg per meter cube. Similarly, the viscosity of the oil is given, so which is written as mu p, 3 into 10 raised to minus 2 poise, and it is flowing at a rate of 3000 liters per second, which is 3 meter cube per second. Similarly, the tests are conducted. So now when the tests are conducted, tests are always conducted on the model. So 15 centimeters diameter pipe will become the model. So dm is 0.15. Here water is used, so specific gravity is 1. So therefore its density has to be 1000 kg per meter cube. So you have to find the velocity, that is velocity in the model, and rate of flow in the model. You have to take viscosity of water as 0.01 poise. So therefore the viscosity in the model is 0.01 poise. So now since it is the application of Reynolds model law, so therefore the Reynolds number in the model should be equal to Reynolds number in the so so this is the equation. So we are required to find the velocity in the pipe. So since we want here, so therefore we know the discharge in the prototype. So velocity in the prototype can be determined. So which is q by respective area. So therefore it is 3 meter cube per second. So diameter is 1.5. So therefore we get 1.698 meter per second. So we can apply Reynolds model law, rho m Vm Lm by mu m, rho p Vp Lp by mu p. So since here in the model water is flowing, so 1000, so velocity in the model has to be determined. So whereas the diameter is given, so because this is again a linear scale, ratios has to remain same. So therefore Lm by Lp or it should be equal to dm by dp. So instead of Lm we write as dm, instead of Lp we write as dp. So therefore mu m is viscosity is given for the model, viscosity for the prototype is given. You can substitute in poise and poise because both are in because it's the ratio. So you can substitute in these two should be in the same units, velocity can be in the same units, density has to be in the same units. So like this, so we get the velocity Vm, because this 1.698 is in meter per second, therefore we get 5.094 meter per second. So therefore discharge in the model is nothing but area, the cross-sectional area pi by 4.15 square into velocity, that gives 0.0899 meter cube per second, which is also 89 multiplied by 1000 will get around 90 liters per second. So this is how we solve solve this problem applying Reynolds model law to get the velocity in the model as well as discharge in the model. So taking another problem, the ratios of lengths of a submarine becomes a prototype, and its model here is the ratio is given as 30:1. So therefore it is not Lm by Lp, it is Lp, because this length of the submarine is more than its model, so 30 times Lm. So therefore it is Lp by Lm is 30 by 1, or Lm by Lp is 1:30. So now here the speed of the submarine is given. So therefore velocity in the prototype is 10 meter per second. The model is to be tested in the wind. Here since a wind tunnel is used, so therefore air is used here. So what is the speed of the air? So therefore velocity in the model has to be determined, that is in the wind tunnel. So you have to also determine the ratio of drag. So that means the ratio of forces between the model and the prototype should be determined. So you have to take kinematic viscosity of sea water. So because submarine is in the sea water, so therefore the kinematic viscosity of the sea water is 0.012 Stokes, and similarly for the air it is for air here 0.012 is for the sea water and 0.016 is for the model. Similarly density for the sea water is 1030 kg per meter cube, and similarly for the density of air in the model is 1.24 kg per meter cube. So that is you have to identify particularly which is prototype and which is model here. So now applying rho m Vm Lm, the Reynolds number in the model should be equal to Reynolds number in the prototype. So this also can be written as Vm Lm by nu m equal to Vp Lp by nu p. So since the kinematic viscosity in the model and kinematic viscosity in the prototype is given, so and Lm by Lp is also known as is also given, which is 1:30. So therefore we can find out velocity in the model, which is 400 meter per second. So the velocity of the air is 400 meter per second. So you know that drag force is nothing but mass into accelerations. Mass is density into volume. Acceleration is velocity by time. So rho into L cube, velocity by time. So therefore this can be written as rho L square, 1 L by T is nothing but velocity. So therefore the drag force can be written as rho L square V square. So now take the ratio, because the ratio of the forces, drag force asked. So that is rho M Lm square Vm square by rho P Lp square Vp square. You know the ratio of the densities, which is 1.24 by 1030. We know Lm by Lp, which is 1:30 square. Okay, so Vm is already calculated, velocity in the model is 400, so 400 square divided by the velocity in the prototype, which is 10 meter per second. So that comes the ratio as 0.00214, or Fp by Fp, that is for the drag force in the prototype to the drag force in the model is 467. So taking another problem where a ship of 300 meters, so therefore the length of the prototype is 300 meters. It is here sea. It is in the sea water whose density. So therefore density of the prototype is 1030 kg per meter cube. So now this 1:100. So that means LR is 1:100 is tested in a wind tunnel. So therefore the model is tested in the wind tunnel. Then the velocity of air, so therefore velocity of in the model, velocity of the model is that is in the wind tunnel is 30 meter per second, and resistance of the model, so therefore Fm is 60, the force in the model is 60 newtons. You have to determine the velocity of the ship, that is Vp, and also the resistance also should be determined in the prototype. So density of the air, because air is used in the model, so therefore density is given 1.24 kg per meter cube. Similarly, the kinematic viscosity of seawater is 0.012 stokes, that is in the prototype, and similarly for air, which is used in the model, is 0.018 stokes. Again using Reynolds model law. So Reynolds number in the model should be equal to Reynolds number in the prototype, which can be written as Vm Lm by nu m should be equal to Vp Lp by nu p. So since we know the velocity in the model, the length of the model, whereas length of the prototype. Similarly, the kinematic viscosity in the model as well as kinematic viscosity in the prototype. So therefore, velocity in the prototype, velocity of the prototype, that is the ship, can be determined, which is 0.2 meter per second. We know the ratio of the forces is nothing but rho L square V square. So therefore, take the ratio. So we force in the model is given. So therefore, force in the prototype can be determined because we know all other quantities. So therefore, the force, the drag force for the prototype will be something around 22,150 newtons. So here water is flowing through a pipe of diameter, so of 30 centimeters diameter. Here the diameter 30 centimeters is given, which is treated as a prototype. So the water is flowing at a velocity of 4 meter per second. So therefore Vp is 4 meter, dp is the diameter of the prototype is 0.3 meters. Find the velocity of the oil flowing in another pipe. So here we have taken where 15 centimeters diameter is taken as the model, where oil is flowing. So therefore dm is 0.15. We have to find velocity. The viscosity of water is 0.011 poise, so mu p is 0.01 poise. Here water is used, so 1000 kg per meter cube. Similarly, viscosity of oil is 0.025, so we are used here. So here specific gravity of oil, which is used in 15 centimeters diameter pipe, so density can be calculated as 0.8 into 1000, which is 800 kg per meter cube. So now here we can we can apply Reynolds number in the model should be equal to Reynolds number in the prototype. So since directly the ratio is not given, LR ratio is not given, so therefore we know that it is Lm by Lp, which is also nothing but the dm by dp, which is the diameters are given, so 0.15 by 0.3. So it is and this ratio can always substitute here. So therefore, what is density in the model, which is 800 kg per meter cube? We can find velocity. So Lm by Lp can be written as 0.15 by 0.3. So here the dynamic viscosity in the model is given, dynamic viscosity in the prototype is given, and density in the prototype is known. Okay, so 1000. So where, and the velocity in the prototype is known, which is 4. So therefore velocity in the model is 37.5 meter per second. Now coming to the next important model law, which is known as the Froude's model law. So where this is used, where gravity force predominant, for example, flow through spillways or flow over weirs, notches, where gravity force is predominating. So now for perfect dynamic similarity between the model and the prototype, Froude's number in the model should be equal to Froude's number in the prototype if gravity force predominates. That means we know that Froude's number in the model should be equal to Froude's number in the prototype. So what is Froude's number? It is nothing but V by root GL. So here, so V by root GL in the model should be equal to V by root GL in the prototype. So that is Vm by root of Gm Lm should be equal to Vp by root of Gp LP. But you know that Vm by Vp is velocity ratio, this is acceleration due to gravity ratio, Lm by Lp is Lr should be equal to 1. Now, since the acceleration due to gravity is same in the model as well as in the prototype, so its ratio is always equal to 1. So therefore, we can write Vr is Lr to the power of half. So this is what you can remember when we apply Froude's model law. So always we have a formula for Vr, which is, so everything is expressed in terms of Lr now. So this is linear scale ratio, which is Lr to the power of half. Similarly, you can express time ratio, which is what is velocity. Velocity is nothing but length by time. So what is time? It is length by velocity. And now the time ratio can be written as TR, whereas length ratios can be written as LR, and velocity ratio can be written as VR. So what is VR? It is LR to the power of half. So therefore, time ratio is also LR to the power of half. Now we have acceleration. We can write the formula for acceleration velocity by time. So therefore its ratio can be taken. So acceleration ratio is velocity ratio by time ratio. So what is VR? It is LR to the power of half. What is time ratio? It is LR to the power of. So therefore acceleration ratio is 1. So now coming to the discharge, that is QR. What is discharge? It is area into velocity. But discharge ratio can be written as area ratio into velocity ratio. But area ratio is nothing but it is AM by AP, which is LM into BM by LP into BP, which is nothing but LR square. So therefore area ratio can be written as LR square. VR is written as LR to the power of half. So therefore you can remember that discharge ratio is always LR to the power of 5 by 2. You can also derive from this discharge is volume by time. So what is volume? It is LR cube. What is time ratio? It is TR. What is TR? Is LR to the power of half. So 3 minus half is 5 by 2. So therefore QR is also LR to the power of 5 by 2. Now coming to the force ratio is mass into accelerations. So what is force? It is nothing but rho. So here it is rho into LR cube. Here it is VR by TR. So but if the same fluid is used in the model and prototype, suppose water is used in here, so then rho r is always 1. So therefore we can write it as it is LR cube. What is VR? It is LR to the power of half. What is TR? It is LR to the power of half. Therefore force ratio is LR cube. Now for the work or energy, torque or moment is nothing but force into distance. But force, if this ratio can be calculated, we can be represented as ER for all these quantities. So therefore FR is LR cube into LR, so which is LR to the power of 4. But this will be used for to calculate power. So power ratio is nothing but work ratio divided by time ratio. So ER is LR to the power of 4. Time ratio is LR to the power of half. So therefore it is LR to the power of 7 by 2. So these ratios which you have determined for all the quantities can be always expressed in terms of linear scale ratio, which will be used in the problems. So where does this Froude's model law finds its applications, particularly in the free surface flow, such as flow of spillways, weirs, sluices, channels like this, or flow of a jet from an orifice or a nozzle, where waves are likely to be formed on the surfaces. So these finds where the gravity force predominates. So problems will be very easy when you try to express everything in terms of linear scale ratios. Here a 1:40 model is given, so therefore LR is 1:40. So here the velocity the in a model, so therefore velocity Vm is 2 meter per second, discharge is again 2.5 meter cube per second. Then find the corresponding velocity discharge in the product. So that's why we have to find Vp, that is velocity in the model, and discharge in the model. But here since we want Vp, so we know that Vr is Lr to the power of half. So what is velocity ratio? It is Vm by Vp. So Lr is given, which is linear scale ratio is given, is 1:40. So therefore velocity in the model is known, so therefore velocity in the prototype can be determined, so which is 12.65 meter per second. Similarly, if you want discharge in the prototype, you can use the ratio QR, that is discharge ratio, which is Lr to the power of 5 by 2. So what is QR? This is Qm by Qp, but discharge in the model is given, which is 2.5. So therefore you can find Qp. So therefore the discharge in the prototype is 25,298 meter cube per second. So that means we are using the formulas for velocity ratio as well as for the discharge ratio. Now we have a 1:50 spillway model, so therefore Lr is 1:50 and has a discharge, that is the discharge in the model is 1.25 meter cube per second. We have to find what is the corresponding prototype discharge, that is Qp. That means since the discharge is asked, we should use QR, that is Lr to the power of 5 by 2, but Qm by Qp is Lr to the power of 5 by 2. So therefore discharge in the model is given, so that will enable us to find out the discharge in the prototype, which is 22,097 meter cube per second. Now it is also asked if the flood phenomenon takes 12 hours to occur in the prototype. So that means in the prototype it is 12 hours. The same phenomenon if it occurs in the model, so what is the time required? So therefore the time ratio has to be used. So Tr is Lr to the power of half. You know time ratio is Tm by Tp. So therefore Lr is 1:50. So here the time in the model is asked. So therefore it is about 1.69 because it takes 12 hours there. So it is 1.69 hours in the model. So if the flood phenomenon which occurs 12 hours in the prototype, it will occur if you build a model and the same phenomenon occurs here, it takes about 1.697 hours. Now a 1:20 model, that is Lr is 1:20. The height of the hydraulic jump in the model. So the height of hydraulic jump in the model is 0.2 meters. You have to find height of the jump in the prototype. So since the height is nothing but the linear quantity, so therefore linear scale ratio has to be used. So therefore linear scale ratio is nothing but it is a ratio of any linear dimension. So height of the jump in the model to height of the jump in the prototype. So 1:20 should be equal to 0.2 by height of the jump in the prototype. So therefore height of the jump has to be 4 meters. Similarly, it is asked if the energy dissipated in the model is point. So energy, though the term energy, but it is a power unit, so it is 0.1 kilowatts. So therefore the power ratio has to be used. So what is the corresponding value in the prototype? So since the power dissipated or energy dissipated is 0.1 kilowatts, so what is the corresponding value in the prototype is asked. So therefore it is Lr to the power of 7 by 2. So don't use the ER ratio, but though the term is confusing, but the unit you have to be careful. So since it is kilowatt, it is a power ratio has to be used. So therefore the power in the prototype is the energy dissipated in the prototype is 3,577 kilowatts. Now we also have a geometrically similar model of a spillway. The discharge per unit length is 1 by 6 meter cube per second per meter. That is nothing but discharge, which is represented as small qm. So it is in the model, which is 1 by 6 meter cube per second per meter. So here the linear scale ratio is given 1:36. You have to find what is the discharge per meter length of the prototype. So qp. So here since the discharge is involved, so therefore QR is used, which is Lr to the power of 5 by 2. But what is QR? It is Qm by Qp, which is Lr to the power of 5 by 2. So now, so leave it as it is here. So we know that discharge per unit width ratio is nothing but Qm by Qp. Okay, but what is this qm? So it is nothing but the total discharge divided by the width or length. So it is the discharge in the prototype divided by the length. So but here qm by qp is nothing but the qr, and here the lm by lp is nothing but lr. So this can be written as this discharge per unit width ratio can be written as this qr divided by lm by lp, which is lr. So what is QR? It is Lr to the power of 5 by 2 and Lr. So therefore it is Lr to the power of 3 by 2. So now I am using this ratio rather than this ratio. So because here discharge per meter width is given, so meter cube per second per meter. So that's the reason why I am using Lr to the power of 3 by 2. So now here discharge in the model per unit width is given, which is 1 by 6, and QP has to be determined, which is 36 meter cube per second per meter. This is a very interesting problem where a spillway models were built to geometrical similar scale of 1:50 across a flume of 600 mm width. Okay, so LR is 1:50 across a flume, okay, of 6. So this becomes the width of the model, and prototype is 15 meters high, spillway is 15 meters high, okay, and maximum head is also given 1.5. So we have to find height of the model and what is the head. So we have to use, since height is involved and head is also a linear ratio, so linear scale ratio has to be linear quantity, so here linear scale ratio has to be used. And if the flow or the model is given, so the flow is given, so it is in terms of meter cube per second, so we have to find the discharge ratio, and from there you have to divide by the length and to get the discharge per meter cube per second per meter. And negative pressure in the model is 200. So this is again a linear quantity, so linear scale ratio is used. So that's how the problems are solved here. So here we have a linear scale ratio is 1:50. So width in the model, that flume width is given, which is 600 mm, which is 0.6 meters. Height of the prototype is given, so 15 meters, and head in the prototype is given. So therefore, since we want what is the height of the model, so we are using linear scale ratio, which is nothing but hm by hp. So 1:50 is given, so we can find out what is the height of the model. So if the height of the prototype is 15 meters, so height of the model can be 0.3 meters. Similarly, the head is also now a linear quantities, so therefore linear scale ratio is used. So if the head in the prototype is 1.5 meters, what is the corresponding head? So it will be 0.03, since we are using linear scale ratio. Similarly, they have asked what is the discharge. So therefore, if the discharge in the model is 12 liters per second, so okay, 12 liters per second. Here we have something like the discharge ratio has to be used, which is LR to the power of 5 by 2. Similarly, if your discharge ratio is nothing but QM by QP, which is LR is nothing but 1:50. So similarly, we have if you use this, so 12 liters has to be converted into meter cube per second. So 12 into 10 raised to minus 3. So you forgot to write here. So 12 into 10 raised to minus 3 meter cube per second. So if you multiply by 50 to the power of 5 by 2, you will get this. So I think this answer is correct. So you just check out for this answer. This has to be 12 into 10 raised to minus 3 meter cube per second. So here, okay, so this is 12 liters. So therefore, corresponding in meter cube per second, we can get the answer by multiplying by 50 to the power of 5 by 2. So but what is asked? So discharge per meter length of the prototype is asked. So what is that QP? It is nothing but discharge in the prototype divided by the length in the prototype. But length of the prototype is not given. So therefore we know that the here LR is nothing but LM by LP, which is also nothing but BM by BP. But here width of the model is given, which is 0.6. So therefore you can find out what is the corresponding width in the prototype, which comes to 30 meters. If the flume is of 0.6 meters, according to this ratio, this width of the channel has to be 30 meters in the prototype. So if you take this quantity and divide by 30, so we'll get meter cube per second per meter. So now here, since the pressure head is asked in the model versus in the prototype, so that is linear scale ratio is used. So 1:50. So here it is given as it is negative pressure head is 0.2 meters. So therefore we can find out what is the pressure head in the prototype by using a linear scale ratio, which comes to minus 10 meters, which is not allowed. Actually the permissible is minus 7.5 meters, which is actually not practicable. So but since the maximum practicable negative pressure head can be minus 7.5 meters, anything goes above 7.5 meters, you know that it reaches vapor pressure. So vaporization of molecules water takes place, where it converts into vapor bubbles, and this will be carried to high pressure regions where they collapse, creating a very high dynamic pressure, which may form cavities on the surfaces, okay, or which may damage the surface. So that's the reason why that's when this negative pressure is not practicable and not allowed. A 7.2 meters and height and 15 meters long spillway. So that means the height of the prototype is 7.2 meters. The length of the prototype is given, which is 15 meters, where the discharge is 94 meter cube per second. It is working under a head of 2 meters, so therefore the head in the prototype is 2 meters. Linear scale ratio is given as 1:9. We have to find out for the model what is the model dimensions. So model dimensions can be height of the model, length of the model, and head in the model. uh, uh, then if the model experiences a force of, that means Fm in the model is, the force in the model is 7500, what is the corresponding force in the prototype? Similarly, since all the linear dimensions are involved, so therefore linear scale ratios are used. So therefore we can use linear scale ratios and find out the height of the model, which is 0.8 meters, for the corresponding height of 7.2 meters. Similarly, if using linear scale ratios, we can find out what is the length of the model corresponding to length of the prototype, which is 15 meters, as 1.67. Similarly, the head in the model can be correspond to linear scale ratio of 1:9. So head in the model, which is corresponding to the height of the head in the prototype, which is 2 meters, can be 0.22 meters. So discharge is also asked. You know that QR is LR to the power of 5 by 2. So therefore the discharge in the prototype is 94 meter cube per second. So therefore discharge in the model can be calculated. So which is 0.387 meter cube per second. We know that the force ratio is LR cube. So therefore Fm by Fp is LR cube. So therefore since the force in the model is given, which is 7,500 newtons, so therefore the force in the prototype can be determined, which comes to this value. So 54,67,500 newtons, which comes to 5467.5 kilonewtons. So all the problems that we solved, yeah, here were of the undistorted the models. So here undistorted models are that which are geometrically similar, that is the scale ratios of the corresponding linear dimensions of the model and prototype are same. So here, since the basic conditions of the perfect similarity satisfy, so the predictions in such models are relatively easy, and the results that are obtained by the model can be directly transferred to the prototype. But there are some distorted models where one or the above terms of the models are not identical to the prototype. For example, if you take a river, when you have a river, so the river width is something like 100 meters, say, and then the depth of water is something like 4 meters. Then if you build the model of the river in the model, so 100 you just reduce it to say something like 1 meter. So what happens to the head will correspondingly, if you use the same scale ratios, the head will be very negligible quantity, which is very difficult to measure. So that time you have to go for what is known as the distorted model, where the vertical scale is exaggerated. That means we give a separate scale ratio for a horizontal, whereas another scale ratio for the model, so that we'll get enough head the depth of water in the model, so that it is easy to measure. So such type of distortion, that here we are trying to distort the geometric property, therefore it is known as a geometric distortions. So we have that's why we have distortions can be like geometric distortions. It refers to distortions of the dimensions. If a different scale ratios are given for horizontal as well as for vertical dimensions, then it's said to be distortions of the dimensions. Particularly in the case of rivers or harbors, reservoirs, where two different scale ratios are given, one for horizontal dimensions, other for the vertical dimensions. Sometimes we give material distortions, where the physical properties of the corresponding materials in the model and prototype are not same. So if you are using for the river models, and we can construct that the river models with the different materials in the laboratory. So particularly useful for the studies of sediment transport. So when we try to distort the material, then it is called material distortion. Sometimes the bed slope in the river is different, and the bed slope in the model is quite different, to get enough slope, and so that we get some velocity, and here so that we can actually predict the results properly. And that's the reason why we have distortion of configuration that takes place. a particular river model where it has to be constructed with a bed slope different from that of the prototype. So such type of distortions which are taking place is either in the form of a geometrical distortions, or maybe in the form of material distortions, or in the form of distortion of configuration. So such models are known as distorted models. Now, taking one example of distortions of dimensions, we have say LRH, which is horizontal scale ratios. Any horizontal dimensions like LM by LP or width dimensions can be taken as LRH. Similarly, any depth vertical scale ratios can be taken with corresponding to the vertical dimensions. For example, height of the model to the height of the prototype, or head in the model to the head of the prototype. So that's we have to identify where we have to use horizontal scale ratios. For all horizontal dimensions we can use horizontal scale ratios, and all vertical dimensions we can use vertical scale ratios. Now we know that velocity scale ratio is VR is Vm by Vp. So what is Vm? We know standard formula as root 2g h is head in the model, where it is head in the prototype. So now here 2g cancels, where it is nothing but root of hm by hp. So what is this hm by hp? It is nothing but a vertical scale ratio, which is LRV. So therefore henceforth we can write it is in the case of undistorted model, we simply used to write LR to the power of half. Here it is specifically it is LRV to the power of half. Now we write scale ratio for area of flow. Area of flow is nothing but AM by AP. So in that here, if you take rectangular cross section, it is nothing but width into the height of water. So BM is nothing but the horizontal, BP is also horizontal. So BM by BP is LRH, whereas HM by HP is nothing but LRV. So henceforth AR is not LR square, it is LRH into LRV for the distorted models. Similarly, the scale ratio for discharge can be written as Qm by Qp, which is nothing but area into velocity. So which is AM by AP is nothing but AR, VM by VP is nothing but VR. So what is AR? It is LRH into LRV. What is VR? It is LRV to the power of half. So henceforth it is written as LRH into LRV to the power of 3 by 2. So for the undistorted model, it is LR to the power of 5 by 2. So 1 plus 3 by 2 is 5 by 2. But specifically for distorted model, we write it as LRH into LRV to the power of 3 by 2. Now comes the scale ratio for time. So velocity is length by time. So time is nothing but length by velocity. So so if you leave a float from from here from one point to another point and measure it time, then length by time will give the velocity. Similarly here we can find out what is the time required. So if you know the velocity, so it is nothing but the linear horizontal length. So LRH is used, so divided by VR. So what is VR? It is LRV to the power of half. So therefore now time ratio is not LR to the power of half, because in the previous case it was LR to the power of half. Now it is LRH divided by LRV to the power of half. Like this, any scale ratios can be determined for the distorted models. So we'll have few examples for distorted models. A discharge through the weir is given as 1.5 meter cube per second. We have to find discharge through the model if the horizontal scale ratio is 1 is to 50 and vertical scale ratio is 1 is to 10. So here what is given is you have to find the discharge, but you know that QR in the undistorted model is LR to the power of 5 by 2. Now it is LRH into LRV to the power of 3 by 2. So what is QR? It is QM by QP. So now discharge in the model has to be given. So QP is given as 1.5 meter cube per second. LRH is given as 1 is to 50. LRV is given as 1 is to 10. So ratio to the power of 3 by 2. So that gives the discharge in the model. So this is how we make use of the horizontal scale ratios as well as the vertical scale. So we can also solve the problem for a tidal model where horizontal scale ratio is given as 1 is to 500, vertical scale ratio is given as 1 is to 50, and what is the model period? So that means the time in the model is to be determined by the time which corresponds to the period of 12 hours in the prototype. We had solved this problem somewhere in the undistorted models. Now we are solving in the distorted models. So TR, that is time ratio, is nothing but LRH divided by LRV to the power of half. What is time ratio? It is nothing but TM by TP. So here LRH is given 1 is to 500, LRV is given 1 is to 50. So therefore if TP is 12 hours is given 12 into 60 into 60, you can convert into seconds. So it takes about 610 seconds for this tide to occur in the model. Now for a river model of horizontal scale ratio, similarly horizontal scale ratio is given 1 is to 250, whereas the vertical scale ratio is given as 1 is to 25. We have to estimate the model value of to a model value corresponding to a prototype slope. So slope in the model has to be determined, where slope in the model is slope in the prototype is given, which is 0.0002, and if similarly the model velocity and the discharges are also given, so we have to find what is the corresponding velocity and discharge. Here slope is nothing but vertical to horizontal. So what is slope ratio? It is vertical, that is LRV, and horizontal is the LRH. So LRV is given, which is 1 is to 25, LRH is given 1 is to 250. So therefore what is slope ratio? It is SM by SP. So since that slope ratio is coming to 10, so it is 10, so therefore slope in the model can be determined, which is 10 into slope in the prototype is given, so which comes to about 0.002. So therefore the slope in the model is quite different from the slope in the prototype. Similarly, the velocity in the model is 0.5 meter per second. So therefore, we are using VR, which is LRV, not LR to the power of half, is LRV to the power of half. So therefore, velocity in the prototype can be determined, which is 2.5 meter per second. Similarly, discharge can be LRH into LRV to the power of 3 by 2. So therefore, what is discharge ratio? QM by QP. So therefore, the discharge in the prototype can be determined, since discharge in the model is given as 0.02 meter cube per second. So LRH has to be substituted as 1 is to 250, LRV is 1 is to 25. So therefore we'll get discharge in the prototype, which is 625 meter cube per second. So these are the problems that were discussed on undistorted models as well as on the distorted models. There is one last topic which is on the model studies, which is known as the scale effect. So all this time I was discussing about the dynamic similarity between the model and prototype, where one particular force was predominating. If viscous force was predominating, I was using Reynolds model law, and if gravity force was predominating, then I was using the Froude's model now. So therefore that's the reason why we have some scale effect that is taking place. If complete similarity does not exist between a model and product, there will be some discrepancy. So if there is, because now we are trying to satisfy either one of the predominant forces, either it should be gravity or it should be viscous or like this predominant force, and so if the complete similarity doesn't exist between the model and prototype, there will be some discrepancy between the results that is transferred from the model to the prototype, and this disturbance or the discrepancy is known as the scale effect. So now we have studied that for the complete similarity between the model and prototype, any model have to be satisfied. So that's what I said, that if viscous force is predominating, then we have to use Reynolds model. If gravity force is predominating, we have to use Froude's so here Froude's model now. So the variables that is having a secondary influence for is neglected generally. So there may be some influence of viscous forces also. So when we take both the effects, then that means where we're taking Froude's model, we are neglecting the other variables here. So only gravity force we are taking into account. So by neglecting these variables, we are trying to have some discrepancy, which is known as the scale effect. So that now, for example, so if both gravity and viscous forces are predominating in the flow phenomenon, then Froude's model law as well as the Reynolds model law should be applied. So take such a case. Now we have already studied in the Reynolds model law, that is VR LR by nu R is 1. Okay, but according to Froude's model law, what is VR? It is LR to the power of half. So when I take this VR, so here it is, if you substitute here, so from one end to, if you combine this Reynolds model and Froude's model law, so then we have what is VR? It is LR to the power of half. So LR to the power of half into LR is equal to nu R. So it is LR to the power of 3 by 2 is equal to nu R, is the new equation that we got when we combine both Reynolds model law as well as the Froude's model law. So now what does this equation 3 indicates? Okay, what does this equation 3 indicates? Now equation 3 indicates that now you select any model here. Okay, your model scale. So for example, R, so it will not be 1 is to 100, any scale. Say, so for example, I take 1 is to 100. So 1 is to 100 to the power of 3 by 2, we will get nu R. So that means we get a nu R ratio, that is a liquid of appropriate viscosity has to be selected. Now suppose I used mm, I use water in the prototype. So then what will be according to this ratio, because we have taken 1 is to 100 to the power of 3 by 2. So nu m by nu p. Nu m is, we know the viscosity of we have to find viscosity of the liquid in the model to viscosity of the prototype, because we are using water. So we know viscosity of the water. So it gets multiplied with this ratio. So then we have to go on finding the viscosity of a liquid which has got the value according to this equation, which is very difficult to find out. So that's the problem. So now this is the other way around. If we are using the same liquid, if you are using the same liquid in the model and prototype, what happens to nu R? So nu m by nu p, both model and prototype, the liquid is same. So LR here, what happens, this ratio will be equal to 1. So what happens to the linear scale ratio? It will be equal to 1. That means you should build the model as large as the prototype, which is impracticable. So that's the problem it happens when we try to combine any two laws. So therefore it is very impossible to find liquids of any desired viscosity according to this equation. That means if you select a scale ratio, we should go on finding that liquid which has got the viscosity according to this equation. Or if you take same liquid in both model and prototype, then their linear scale ratio will be equal to 1. Then we have to do the something like on a full scale models, which is impracticable. Or if you take you decide which liquid has to be used, then you will get some impracticable or odd scales models, so which is quite impracticable. So under such circumstances, the investigator is forced to construct the model based on one particular law. Either he has to construct Reynolds based on Reynolds model law, or based on force model law, depending upon which force is predominating in the flow phenomenon. So if he does that, then will be neglecting the other the secondary influence on the secondary influence, which may cause the scale effect. So by following one predominant forces, by neglecting the secondary influence on the model, still we can transfer the results without any appreciable error. So that's how all the models are constructed based on one particular model law, depending upon the forces that are predominating in the flow phenomenon. So this is about the model studies, where we discussed in detail about what is why models has to be constructed. Then we also discussed about the similarities, which is geometric similarity, dynamic similarity, and kinematic similarity. And we also discussed about the ratio of the forces which led to dimensionless numbers like Frost number, Reynolds number, Mach number, Weber number, and Ehlers number. And also we discussed about the various model law, the Reynolds model law and Froud's model law, and so we solved some few problems on Froud's model law as well as Reynolds model law. So if you I will be uploading this on my YouTube channel. You can subscribe to my YouTube channel and view my lectures, and this is the link that you can always click onto that, and also click the notification button, so that you will come to know about the latest updates that I will be uploading on various civil engineering topics. So thank you very much. If you have any queries or any suggestions or any comments, and if you can give feedback, you can always contact me. I'm professor in the Department of Civil Engineering at KLS Institute of Technology, Belgavi. And you can also mail me to this mail address, R.SHREEDHAR@GIT.edu. Hope you found this model studies to be quite interesting. This was my 21st online video lecture, so which will be uploaded on to the YouTube. I will be leaving more and more YouTube videos which you can make use of for your any competitive examinations. like gate or engineering service exams, or you can also use for any technical interviews, for any good companies that come to your campus. Hope you will go through all these videos that I have uploaded onto my YouTube channel. Thank you very much.